Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Jake Lustig-Yaeger with us today. Hello, Jake.
Hi, Frank, and hi, everybody.
A little bit of bandwidth lag there, but that was okay. And Jake, where are you located at?
I work at the Johns Hopkins Applied Physics Lab in Laurel, Maryland.
Very cool. Let's see. And it is November 28th, 2023 as we record this. And is there snow on the ground yet in Boston or Baltimore?
No snow on the ground.
No snowman. Maybe for Christmas. It'll all be good. Super. Let's see. And Jake, what do you like to do for research?
I'm trained as an exoplanet astronomer, so I study planets that orbit other stars and mostly characterize their atmospheres. And in the process of studying exoplanets, I study solar system planets as a ground truth for what we expect to learn about exoplanets. And so that has brought me to studying the Earth as well as Venus, as we'll discuss a lot more today.
Very cool. Very cool. And that is going to bring us to this very awesome PSJ article. It is open access. It's the open access era, people. You can go get a copy for free. Go grab one. A WISPR of the Venus surface, analysis of the Venus Nightside thermal emission at optical wavelengths. And Jake, take us away.
Great, thanks, Frank. So this is a collaboration both between multiple institutions and different types of science that NASA conducts using Helio Science Mission to study Venus planetary science with a team of heliophysicists, planetary scientists, and astronomers. So this collaboration involves my colleagues Noam Eisenberg, Laura Mayorga, and Aaron May from Johns Hopkins Applied Physics Lab, Marty Gilmore from Wesleyan University. Whoops, I skipped over Angelos Vorlidas and Philip Hess, Brian Wood, Russ Howard, Noor Raufi, all from the Parker Solar Probe mission team, and Jada Arni from NASA Goddard.
Nice.
So this has been a fantastic collaboration of folks to work with.
Good shout out. All right.
And this paper is all about analyzing sort of serendipitous observations of Venus made with the Parker Solar Probe's the camera that mission has on it, which is the wide field imager for solar probe. So that's the WISPR acronym that we're going to be throwing around throughout this whole thing.
I love it. WISPR. Good. The Venus WISPR.
Exactly. And for people keeping score at home, the WISPR of a Venus surface is really kind of an homage to Whisper of the Nameless Fear from the Lord of the Rings. It's kind of a quote there. So for those big Tolkien Lord of the Rings fans at home, that was all. That's for you guys and us, of course.
Very cool.
Lord of the Rings.
Very cool. Love it. Okay, let's get to WISPR.
Yeah. So WISPR is this great instrument used to study the solar corona. And I think one thing that as non-heliophysicists was a misconception for me when I first learned about the Parker Solar Probe is that even though it orbits the sun and studies the sun, these WISPR cameras are designed to study the very faint solar corona. So even though the sun is so bright, the WISPR instrument is used to study very faint emission from the solar corona. And that is a key feature that we took advantage of in studying Venus during this flyby.
Cool.
So because Parker Solar Probe needs to conduct its science of the solar corona, it's used a series of Venus gravity assists to change its orbit to get closer to the sun throughout its mission. And so, yeah, so it's so common for interplanetary spacecraft to use Venus gravity assists to modify their orbits, which is just a great feature. And many of those planetary missions, Parker included, have cameras on them and can take pictures of Venus while they're in orbit. And so that's been true of Galileo and Cassini missions as they orbit. Yeah, Frank, do you have a question?
No, I'm just engaging. Go ahead.
Okay, great. So the really fascinating thing about WISPR here is that these cameras operate in the optical and sort of around 650 nanometers to about 780, 800 nanometers. So in the red optical to like really near IR. And when it observed Venus's night side as it passed into the shadow of Venus in its gravity assist, these cameras observed Venus and were able to see straight through the atmosphere of Venus. And what was seen in the images was thermal emission from the surface of the planet. And because the thermal emission map perfectly reproduced known structures of the elevation map of Venus, we knew we were seeing straight through the clouds to the surface beneath, and basically tracking the temperature variations of the surface of Venus. And Venus is a planet just completely enshrouded in clouds, and so it's challenging to observe the surface of Venus, and that dates back to the history of studying Venus from the Earth. But it was actually discovered in 1984 by this paper, Allen and Crawford, that you can peer through the atmosphere of Venus from these night side opacity windows. And these windows are band passes in which the atmosphere of Venus is optically thin, allowing thermal emission from the surface to just stream out of the atmosphere to remote observers. Cool. And these are really challenging observations to make from the ground, because the night side of Venus, when you see the night side of Venus from Earth, the sun is always right there, and you've always got some crescent that is much, much, much brighter than the day side, or much brighter than the night side. So it's very challenging to make these observations, but they can be made from spacecraft, particularly in orbit, that pass into the night side.
Cool.
So that's exactly what Parker did here. And so we published a paper last year, Wood et al. 2022, that validated. We used some thermal emission models, and we looked at the instrument properties, and we validated that indeed thermal emission is coming from the surface through the atmosphere, and these are indeed the shortest wavelength night side observations of Venus ever observed. Cool. And so this paper is all about digging deep into those observations in the series of images from the 2021 flyby, and analyzing the geology and figuring out what can we learn about the surface of Venus from these new type of observations using this heliophysics mission, and can we sort of use that to motivate more future work and insights into Venus, because it's never been observed at this short of wavelengths on the night side.
Awesome. Very good. Very cool. Okay. Well, it's got a trajectory here. Let's talk about the trajectory first. Where are we looking?
Yeah. So this is a top-down view of Venus with we've got the axes in kilometer, or in 1,000 kilometers and units, and the sun is going to be in the negative y direction directly. Okay. So if you look at Venus at the origin, the sun is just kind of down. And we can see the trajectory of the Parker Solar Probe mission. You can see it deflect ever so slightly from like left to right as it gets to the sort of point of closest approach to Venus. And that's that trajectory adjustment that the Parker Solar Probe mission was the point here. But the dots shown here in both blue and sort of green are where images were taken with the WISPR inner camera and the WISPR outer camera.
Okay.
And so these two cameras are pointed such at an angle from one another. So typically they can observe sort of, they're not looking at the sun when it orbits the sun, but they observe like 30 degrees off the sun and, a couple tens of degrees further off of that. So there's what the inner camera observes typically closer to the sun, the outer camera observes the corona further from the sun. And here you kind of get the series of images kind of where WISPR outer sweeps over Venus and then WISPR inner sweeps over Venus. Kind of, you can see that WISPR I inner kept taking images a bit further along the trajectory line than the WISPR outer camera.
Right.
And due to some complexity in the distortion model of these particular cameras, we focused this investigation largely on the outer camera. Those images came out really clean from the February 2021 flyby. Nice. And we've left to future work study of the inner camera, which is kind of just buried in the disk of Venus and has some great features to it. But it's going to be a whole nother paper to look at that. So we can talk a bit more about that going forward. But that's kind of the trajectory setup and a series of images taken.
Okay, good, awesome. Okay, that's our geometry, that's our flyby. And we talked about WISPR. You want to talk about the data reduction at all? WISPR reduction? Coordinate transforms?
Well,
it's up to you.
I'll speak briefly about it. I'll say that I'm not an expert on the WISPR reduction. That was conducted by our brilliant Parker Solar Probe WISPR team members who are just experts in how the WISPR data are collected and all of the subtleties of that. So we really worked from the WISPR level 2 image data that are publicly available and hosted by NRL and their website. And really, I just appreciate those colleagues for their expertise. And really, a project like this is hard to do without an interdisciplinary group of folks who specialize in different things. And I think that's just like the best part of a project like that is collaborating on stuff that any one individual wouldn't be able to do, but the team can do together.
Awesome. Good. Super. Good. Okay. We got some transforms. Ooh, we got a sequence. This is from the outer camera.
That's exactly right. Yeah. So we saw in the trajectory plot the blue dots where the WISPR outer images were taken. And this, so we can touch on that briefly. So this series of images that we'll look at are those blue dots there.
Oh, what was the, well, I guess I'll see it in this one, the cadence. Here we go. Okay. Yep. Wow. Yeah,
so the entire flyby itself was only about 5 minutes or so. And the exposure times were roughly 3 to 4 seconds. They were real short exposures, but the spacecraft is moving so fast during the flyby that even a 4-second exposure time has some amount of motion blur in it. Yeah. And so we corrected for that a little bit, and I'll talk about that in one of our next plots, but it kind of, there's already some blurring from the atmosphere. Light, although it can escape the atmosphere from the surface, the thick atmosphere does scatter the light and effectively blur the surface features. And so here, basically, from left to right, this is, as a function of time, and we can see some of the same bright and dark features on Venus sort of pass in and out of view here. And exactly. But the star field remains fixed, so you can see that the pointing is stable, but the spacecraft is what's moving here.
Right. Very good. And what's our distance here? So closest approach were 500 kilometers or so. Is that about right?
Yeah, I think that is about right.
Yeah. Okay.
Yeah.
Cool. Okay. there's our sequence of images from our 14 dots there. Okay.
And so one last thing I would say about this image before we move on is another key feature that we're seeing from one image to another that is remains static is the bright rim.
Yes.
So the rim of Venus here has excess brightness. We'll talk a lot more about that, but that is that's mostly due to limb brightening from oxygen night glow emission. So there's not just thermal emission here from the surface, which creates the light-dark contrast, but there's that oxygen night glow at the rim.
Very nice. Thanks for bringing that up. Very good. Okay. Cool. Onwards. All righty.
Onwards.
Let's see what we got. Okay, more data. Then we get into some of the smart radiative transfer modeling.
Yeah, I think I'll probably pepper in descriptions of the methods kind of as they become relevant for the figures, but mostly, you know, this project, the methods can be sort of summed up as the data reduction of the images and the image processing, the correlating surface features with known surface features of Venus and data sets from particularly the Magellan mission, which we'll look at in this next plot, and then modeling the thermal emission from the surface of Venus using a radiative transfer modeling. So there's kind of this data analysis, like pure data-driven analysis part, and then there's a modeling and comparison to models part of this paper.
Very nice. Good. Okay. Got it all. Okay.
And I think this figure 3 is a good place to talk about kind of how we go about looking for correlations between between the WISPR brightness and known surface features. So the left plot is just one of the WISPR O images. I think it was the first image in the flyby. Yes. And then the middle panel is the elevation map, kind of inverse grayscale colored relative to WISPR brightness, where dark regions here are high elevation and very light regions are low elevation. That color scheme flip was done to match the kind of color scale of the WISPR brightness, so the eye can see that the features are just, the correlation is so stark, it's apparent by eye here that this bright spot in the WISPR image is corresponding to this low spot in the elevation. And that is a smoking gun for thermal emission from a surface. The rightmost panel is the radar emissivity from Magellan. And it's a bit more subtle how radar emissivity correlates to everything. Radar emissivity is more of a probe of surface composition, and it's not directly related, or there's no expectation that the radar emissivity should be the same as the thermal emissivity that drives the emission from the surface, but it is a key parameter that we had access to that we kind of carried throughout this work to see if there is evidence of compositional differences via the radar emissivity. So it doesn't track quite as clearly with what's happening on the left, other than where it looks very similar to the elevation map.
Right. Okay, cool. I'm with you. Good.
Perfect.
Awesome.
Yeah, so I think we can move forward here. I could chat briefly about this equation.
Okay.
Just to sort of say that when we do our radiative transfer modeling, a key part of that is converting simulated radiances to counts per second observed by the spacecraft. And so we did all our work in these units of digital number per second, dn per second. And we can just calculate that by using some known parameters like the detector gain and the angular extent of each pixel. And really the key piece of this is the R term, the radiance in the integral there. We'll just, it gets convolved with the effective area of the WISPR cameras so that we can convert any predicted or measured radiance into expected counts by the WISPR cameras.
Okay.
And this is really,
Yeah.
it's relatively simple, and it's just a convolution so that we can verify that predictions of thermal models are consistent with the observations that WISPR was able to make.
Yes.
And we also use this equation to verify that the stars in the background field are consistent with the WISPR counts measured, so that we aren't subject to any weird light leaks that may otherwise explain these observations if there was sort of a less exciting means, which would have been a leaking of light from, say, longer wavelengths rather than light emerging from the atmosphere at sort of new, shorter wavelengths than expected. So we do have a handful of lines of evidence that this is in-band flux. And so some of those lines of evidence were presented in Brian Wood's 2022 paper. But here we added to those lines of evidence with this next plot, where we looked at the star field and validated that the flux received from the stars is consistent with what we would expect from models of these known stars. And so this figure kind of summarizes the analysis here, where you can see in this upper left image, one of the WISPR images, where Venus is at the edge of the image so that we have more stars in view. Those stars are circled and colored corresponding to their spectrum shown on the right, and then they have their stellar HI-HIP numbers listed as well. So those are circled. We then, on this panel to the right, we convolved each of those stellar spectral models with the WISPR bandpass using that previous equation, and we're able to calculate the expected flux from such a star. And we, in the bottom plot, can do a ratio of was it measured to expected?
Right. Yeah.
Measured divided by expected. And they, it's not perfectly one, but of course these are models. But what we were really looking for were sort of egregious trends that would be expected if there was a sort of systematic leak in that bandpass function. So if there were extra throughput to sort of beyond 800 nanometers from this WISPR bandpass, or short of about 500 nanometers, then we might expect the systematic trend, but we don't see that. And so we're confident in saying that WISPR is making measurements that we expect, and there's sort of no surprises here. And so in addition to some of the other lines of evidence, that included analyzing the flight spare of the WISPR instruments and the consistency of our thermal models, as we'll see sort of later down. These three independent lines of evidence suggest that we're seeing thermal emission from the surface of Venus at exactly the wavelengths we expect based on this WISPR sensitivity curve. So flux between about 500 and 800 nanometers, which is predominantly dominated by thermal emission at the longer wavelength of that bandpass when we're looking at Venus.
Yes. Let's see. The 714 refers to an image number? That's a guess.
Yeah, that's right. That refers to the
just an image number, right?
Let's see.
Oh, here we are. Here it is.
One of the image numbers.
Yeah. Okay, got it. There's not 714 stars in that picture. Very good.
No, not so, and it's not quite the same numbering scheme as the previous plot, but it's the sequence where they were kind of numbered on their own, sort of within the canon of this paper, as opposed to within the header of these specific images.
Okay, good. I'm with you. And you got a good spread here on the effective temperature of your stars here, so you get the you can check the leak across. Very good. Okay. These are fluxes from Phoenix stellar models. Okay, gotcha. I'm with you.
Yep.
Okay. And let's go ahead and
perfect.
Figure 5 contours. Ooh.
Yeah.
What do we have here?
So this is a figure we definitely have to unpack here.
Yeah, this has got quite a bit to it. Okay.
And it's a switch of gears from the stellar models. So here we're looking at correlations between the WISPR brightness and the known elevation and emissivity. So this four panel, it's easiest to start in the upper right with the WISPR image.
Okay.
And this is not just an image, but it's a color legend as well, a spatial legend and color legend, because each of these colored regions corresponds to a different geologic unit on Venus that have been mapped and studied with other in the Venus literature extensively. So we have in sort of teal, we have Avda Regio, one of the tesserae units. In yellow, we have Thetis Regio, another tesserae unit, very similar properties to Avda Regio. And then the dark blue or purple is Hastabad, Hastabad, which is another tessera region unit. And then the two circles of the lava and the plains are both sort of associated with the Niobe planitia, but the lava is a kind of maybe an ancient or not clear how old, but not an active lava flow, but a lava plain at very low elevation. And it is slightly lower elevation than the plains unit, but it is anomalously bright. We see it in the WISPR images. So we drew that aperture so that we could track that throughout the study and kind of compare it to the plains unit, which is quite representative of it. They're very similar, but clearly the plains unit has an excess brightness in the images themselves. So to kind of bolster and look at those claims statistically, we show these series of contour plots where the left column here shares an x-axis, radar emissivity, and the right row shares the y-axis of elevation. And so the bottom left image is just a plot of the two reference data sets, the Magellan elevation data versus the radar emissivity data for these regions. So it actually has no information from the WISPR cameras in it. It's just the pure relationship between elevation and radar emissivity on Venus as seen by Magellan. Now, it's the upper left and the bottom right where we bring in the WISPR brightness data to see how the correlations emerge. And so I'll start on the bottom right here where we're looking at elevation versus WISPR brightness. And the big trend here is just the sloping curve from that kind of all of the units share in common. They kind of connect the trend where lower elevations have higher WISPR brightness and higher elevations have lower brightness. And this inverse correlation is exactly what we expect for Venus and has been observed many times. This is because the temperature structure of Venus is such that it's hottest at the surface, just like on Earth. Typically, it's hottest at the surface, and as you go to high altitude, it decreases in temperature following the adiabatic lapse rate. So high altitudes tend to be colder, and that's exactly what we see here, borne out with tons and tons of pixel data and reproducing what's been seen with many spacecraft and ground-based observations. Where it starts to get a little bit interesting is that we get this kind of bifurcation and this fork between Thetis and Avda, where they have sort of different slopes between elevation and WISPR brightness, but they are otherwise quite similar. So this actually, you can see it also in the upper left where we're looking at the radar emissivity versus WISPR brightness, and you can just see that systematically darker brightness for the Thetis Regio. And so this caught our eye because it suggests that something is causing them to emit with slightly different brightness, despite having quite similar elevations in radar emissivities. And we can see that in the bottom left, that the teal and yellow sort of contours do have a significant amount of overlap. While it's not perfect overlap, it's significant. It's significant, and we delved into that in a bit more detail in the next couple plots
Yes,
that really look quite similar to this, because they are at different angles. They're at different emission angles,
right.
the Avda, Regio, and Thetis, and different parts of the image. And so we wanted to take that into consideration. We also see that Avda has sort of a broader extent of elevation in radar emissivity. It extends to a bit lower elevations and a bit higher elevations as well. So could that be causing this? That was something we needed to look at.
Right. Very good. I'm with you. Very good. Okay. We have a mystery there, so we'll dig into that. Figure 5. This is the plane.
Exactly.
And 6. So we're going to bear down into this one. Okay. Figure 6. Or 7 if you want to cover them.
We'll start with 6. I think it has at least one interesting difference here, which is that upper right panel. And the reason we're not looking at an image of Venus here is because this plot shows the same, pretty much the same data, but now for all of the approximately 12 flyby images that had a substantial amount of Venus in the frame. So we combined all of the WISPR brightness data and plotted the same trends. And so in the upper right shows now the emission angle, so the angle between the surface normal and the spacecraft. And as a function of now, or we're looking at WISPR brightness as a function of that. And this is where we can see a really substantial limb brightening effect towards at high angles. So this dashed black line kind of shows roughly where limb brightening starts to become important. And that is a cut that we made for the other panels and for actually the previous plot as well. We omitted emission angles greater than 60 degrees so that we could focus on the surface emission rather than be distracted by the excess brightness from the limb.
Good, I'm with you. Okay.
But this plot itself isn't great for looking at the difference between Avda and Thetis, even though it is there. The bottom left panel shows a way broader extent of surface elevation and radar emissivity data for Avda than Thetis. So that's why in the figure 7 we created a zoom in where we isolated data where Avda and Thetis have significant overlap and where they both overlap in emission angle. So this is a little bit confusing, but the key points are that in the lower left panel, we have selected for these boxes are where Avda and Thetis overlap significantly in elevation and radar emissivity space.
Got it.
And in the upper right panel, we also made this restriction in data to focus for Avda and Thetis between 20 and 30 degrees, where you can see the teal green color and yellow there. And compared to, I guess, if we flip over to the left plot, you can see that other than that one region, they kind of cover a very different emission angle extent.
I'm not boys out, so I get I see.
Does that make sense?
Yes, I'm with you.
Cool. Yeah, so we focused on that region, and when we look at that restricted data set, we still see that kind of bifurcation between Avda and Thetis. It is lower statistical significance because we have cut so much data from this, but it does appear to be there. And so this is like a hint that there could be a different underlying brightness for these two regions as seen by WISPR, which could be due to either initial starting composition or a different history of weathering of those surfaces, or different mineralogical compositions or grain sizes. So it's not like a definitive detection of something, but it's a hint that these regions may be different and something that can be followed up on
Yes.
by future missions to
We'll cover
Venus,
them.
including Da Vinci and Veritas. And yeah, and so it's a kind of an exciting hint that there may be some interesting geology at play here on Venus, and it's cool that Venus, or that the Parker Solar Probe WISPR camera has sort of picked up on something
Picked it
unique.
up. Yeah. Yeah. Serendipitous. Very cool. Very good. I'm with you. Okay.
Exactly.
Onward. And surface elevation.
So now we're kind of switch gears and talk about that modeling that I mentioned, where we're running radiative transfer models
Yes.
to see if the WISPR brightness agrees with what we predict from robust models of Venus.
Yes.
Here we're looking at the WISPR brightness as a function of surface elevation. And so what we did in this thermal emission modeling was we ran a grid of Venus radiative transfer models as a function of elevation, where we took the temperature profile of Venus and we truncated it at different altitudes, so that the emission was higher at those lower altitudes, and the emission was darker, lower flux at the high altitudes. And we convolved those spectra with the WISPR bandpass, and the yellow curve is showing basically the result of that as a function, the result of the WISPR brightness as a function of elevation from just the pure convolution.
Yes.
And it has no correction here. It under predicts the flux a bit.
Okay.
And
yes.
So so we needed we needed some excess flux to explain why our radiative transfer models are slightly under predicting at 0 kilometers, at like the mean radius of Venus. It's decently in good agreement. But as we get to higher altitudes, it's not quite as good. And so I think we should flip to this next plot so that we can be able to explain where these blue curves come from.
Curves. Okay, so that's these three. Keep those in mind. Okay, good. 9. Okay. Okay.
Great.
Okay. Back that off. Okay.
Perfect. So here we're looking at
yes.
A subset of the data at just high elevations. So we selected for only pixels that were known to be at high elevations above 5 kilometers, where the thermal emission should be very, very low. And just for reference, we're showing the radar emissivity here. It's not a particularly important panel, and the emission angle, which varies a little bit over this range, but not a huge amount. And the right histogram poking off the right of the plot shows the stats of flux, where here observed by WISPR, where we expect almost no emission from the surface, or very little. And we can see this number of 16.1 plus or minus 1.4, and we take this to be this value of the average brightness across at sort of low-ish emission angles.
Now you can correct for
that.
Okay.
We can correct for it. So we did subtract off what our thermal emission models said it should be at this elevation, which was not quite 0. It was maybe
offset a little bit
somewhere in the text here, but we're left with an excess of about 9.5 counts per second of sort of unexplained flux at the center of the disk. I think while we can't exactly say what this excess flux is because of the intense limb brightening from oxygen night glow seen at the limb, it's the premier candidate explanation for this excess flux. It's not a huge amount of flux. It just requires there to be night glow, not just at the limb, but also at the disk of the planet. Other explanations could be deviations in the cloud opacity in our models. We assumed sort of the average Venus cloud opacity.
Got it.
And if the clouds were were sort of half as thick, they could let more emission through, and then these models could be brighter. But if we just apply this empirical correction to the thermal emission models, we can go back to that previous figure 8 and see that things are looking pretty good with that correction. We kind of nail it.
Okay, and there's your ±3 sigma. Let's blow that up. But right, so here it is. There's our correction, and this is ±3 sigma off that correction. Okay. Okay, that looks pretty good.
Yeah, so we're happy with this. It's our thermal emission models. They also, they're clearly reproducing the slope of this trend, the kind of the curve and the flattening, which is really nice. It didn't require any sort of weird manipulations to the rate of transfer. It was just, I took a standard Venus one-dimensional atmospheric model and ran this grid, and it fits quite nicely with an empirical correction here.
Nice. Beautiful. Beautiful. Okay.
I think this will bring us to sort of the final plot where everything comes together here.
Yay. Okay, here we go. I'm going to leave this one large unless you dig in, and we'll zoom in. Okay.
Yeah, so now we kind of wanted to put all the pieces together, and so the left panel here just shows a representative one of our WISPR images. This is the third one from the series of flyby images. And I took, yeah, exactly. And so that the next panel shows those radiative transfer model results mapped onto the Venus disk here. And so we can see that it is a little bit darker. That's that missing empirical correction, but it does have the dark regions, the light regions, and kind of all of the subtle features that are present in the WISPR image, except for the limb brightening, are in this thermal model. And that's driven by the temperature of the surface. That's it.
Cool.
And so then we subtracted that thermal model off the image and fit the residuals with a sort of high order polynomial that could capture this immensely steep rise at the rim, at the limb of Venus, but then also fitting the sort of excess at the disk center. So that's what's shown in this middle panel here. And so when we add that excess polynomial fit for the limb brightening to the thermal model, we kind of end up with this thermal plus poly panel. This is the kind of final image model, which does a better job of reproducing the image. So by eye, I think this is really satisfying to sort of see the story come together of the paper. But also the residuals panel is nice because it demonstrates that our residuals are pretty small here. They are Gaussian distributed around 0. And yeah, they're close to 0. Of course, the regions that have an excess of brightness in the images, which are red, and the regions that are dark, tell a kind of interesting story. Clearly, we're not quite hitting the limb of Venus perfectly here with this correction. And also that bright spot. Yeah, exactly. That lava flow is brighter than we predict, which is also interesting. So we don't have any sort of firm explanation for these residuals. They are still small. It could be compositional, it could be clouds, it could be patchiness in the night glow emission as well. These are things that are not a crazy explanation. Venus does exhibit cloud opacity variations and some patchiness in the oxygen night glow. So a combination of these factors could be what's explaining it to some degree. And it's really a sort of a pleasant final way to put a straw in the cap of this paper and show that the observations are really seeing thermal emission from the surface, and that it kind of leaves some interesting questions for future works.
Indeed. Yeah, that is this is an awesome sequence. Great money shot. Very good. Okay, we got some of the night glow parameters on how we correct for night glow. And there is a really awesome, short, but awesome appendix people should check out. Where are we here? The appendix on the data availability. Oh yes, you talk quite a bit of the opacity variation. So there's a study there on the opacity variations of the atmosphere. Very cool. Okay.
Yeah. Yeah, the appendix, this table is yeah, we were just looking at it because we held the clouds fixed throughout the primary modeling of the work, but we did want to look at what happens if we change the individual modes of the clouds, because this is a 4-mode model, and kind of just looked at how if we remove the cloud entirely, how it changes the flux in the WISPR band, and how it changes the flux in the more well-studied 1-micron opacity window. And so we see, I think kind of the takeaway maybe is seen in the altogether, like if we totally remove the clouds from the Venus model, which is kind of an extreme example. Venus very obviously has clouds, but if we remove them, we would get an excess brightness in the WISPR band.
Yeah. Yeah.
We get about 2.5 times more brightness if we remove the cloud, but in the 1-micron band, we get almost 4 times the brightness, or 3 3/4. And so emphasizing that the WISPR band is sort of less susceptible to the cloud opacities than the 1-micron band, which is kind of cool because this is a new bandpass to study the night side of Venus, and kind of is less susceptible to obscuration by clouds, which is kind of brings it back full circle to why Parker Solar Probe and the WISPR camera was able to make these observations in the first place.
Yes. Very cool. Nice loop. Nice loop. Awesome. Jake, I want to thank you so much for walking us through this very awesome article. Very nice. Thanks. Let's see. And you touched on—
my pleasure to be here and walk through it. Thank you.
Thank you. You mentioned it a couple of times there with some teasers. And so let me go ahead and push on that a little bit. On where do you think we go from here, let's say over the next 2 to 5 years, maybe decadal if there's new missions, given the published paper. So is there additional solar Parker WISPR images waiting, just sitting in the can, waiting to be analyzed? Is there other future missions? Could the theoretical modeling be improved? Things along those lines. So just sort of next steps.
Yeah, I'd say yes to all. So there are a few more. As we mentioned, we didn't study in this paper the WISPR inner camera images, the WISPR eye. And so those images we will be analyzing and in a forthcoming paper, along with some of the flyby images from July 2020. So combining from multiple flybys. And then perhaps the most exciting thing is that about a year from now, Parker Solar Probe will conduct its final Venus gravity assist around Venus, and it will be even closer to Venus. And so it's going to have this very close flyby just above the atmosphere. And we have been working with the Parker Solar Probe team to optimize that. There's not too much wiggle room. We obviously don't want to disrupt their trajectory assist, their gravity assist, but we can make some amazing images. Everyone's really excited about this next flyby. It will be observing a different portion of Venus, so we won't get sort of another look at these interesting surface features, but we will get an opportunity to kind of do the same thing on the other side of Venus and in a region that will be studied with the Da Vinci and Veritas missions, as far as I understand. So we can continue to make predictions for those missions going forward.
Cool. Remind me again when that next flyby is. What was the date on that?
It's going to be in November 2024, I believe.
Okay, 1 year, roughly 1 year from now. Okay, cool. Very nice. Well, it'd be really awesome to see that data come down. and see how that fits into the pipeline and is consistent or inconsistent with the side that you got now. And it'll be really good to see the analysis on the inner images as well. I think that'd be very nice. So it'll be really exciting to see this develop over the next year or 2 years. Very cool. Very nice.
Yeah.
Jake,
thank you
so much. I really appreciate you walking us through your very lovely article. And
it was my pleasure to be here. Thanks, Frank.
Thank you. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.